isomers. We're going to practice drawing some isomers. And then we're going to talk a little bit about some chemical reactions in organic chemistry. Just two of those. Mouse species here. There you go. All right, so last time we talked about constitutional isomers, which is you have the same atoms, they're just bonded together differently. That's a constitutional isomer or a geometric isomer. And then a stereoisomer is that they're connected the same way, but they're arranged in space slightly differently. So on your paper, I have this example, but we'll talk about it up here too. So if we look at this, across this double bond, remember the double bond can't rotate. So what I like to do is if I draw a line through my double bond, and I find the two biggest carbon groups, these two carbon groups are on the same side. This is called the cis isomer. They're on the same side of the double bond. And then if I come over here, we have the same atoms. We have 4 carbons. How many hydrogens? 8 hydrogens. And then I find the biggest carbon groups. These are across from each other. So this is in the trans position. These are locked across from each other on the double bond. So that's trans 2-butene, this one's cis 2-butene. They're locked on the same side. So that's a stereoisomer. The only difference between the two types of the two molecules is that the arrangement of the groups is the same. Oh, is there anyone who missed last time that didn't get the chapter 13 note? I think there's a few missed. Did you get that? Okay. Okay. All right. Okay, so the reason this is just because, like last time we talked about, you cannot rotate a double bond. So those groups can get locked either on the same side of the molecule or across from each other. Okay, so this is a pretty common molecule, oleic acid. Have you heard of that before? Sometimes it comes up in nutrition. This is a cis example of a molecule because we have these two long chains and they're on the same side of the molecule. We have the two hydrogens on the opposite side. So these all have the same carbon length. On the left, we have this trans example of the molecule. And this is our cis example of the molecule. They're on the same side. And then this one has no double bond. This one's saturated, has all the hydrogens places filled up. So this is an example of a trans fat versus a cis fat. Have you heard of those from like talking about nutrition? Okay. So our bodies have a harder time breaking down these trans fats. And so if we have these cis fats, those are easier for our bodies to break down. So these different isomers, they have different physical properties. Our bodies react to them differently. So I think it's not just that they are a different geometry, they have also have different physical properties. So that's kind of interesting. All right, go ahead and try to draw these. So one is the trans 4-methyl-2-pentene isomer, and the other one is the cis 4-methyl-2-pentene isomer. So this, both of these have the same number of carbons and hydrogens. You should be able to figure out the parent chain and where the side chains are and where the double bonds are based on what we've already talked about. So see if you can draw these. I'll give you a minute. Okay, have you had a minute? You're still drawing? You ready? Not ready. Okay, I'm gonna start drawing the one on the left. So I think for me, the trans isomer is usually easier for me to draw. So this is pentene. So I'm just gonna draw pentene. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 2 pentene, so it doesn't matter which direction I go. I'm gonna go this way. 1, 2. My double bond is gonna be at the 2, starting at the 2 carbon, the 2 position. So we've got 1, 2, 3, 4, 5. And then my methyl needs to be at the 4 position. And then if I look across a double bond, so I have my double bond, I'm going to cut my double bond in half. My 2 biggest carbon groups are here, this methyl group, and here, this kind of looks like an isopropyl group. And so they are across the double bond from each other, so that's the trans isomer. Does that make sense? Okay, so then to draw the cis isomer of this, what I need to do is I need to get these to be on the same side of the double bond. So I like to just take this methyl group and flip it up here. I could also take this isopropyl group and flip it across the double bond, but then that's just more to draw. So I'm going to draw the same thing here. So I have this double bond, I have this kind of isopropyl group, and then I'm going to take my methyl group and I'm going to flip it across. So then I still have 1, 2, 3, 4, 5. I still have my double bond at the 2 carbon. Let's draw 1, 3, 4, 5. My methyl group is at 4. But if I cut my double bond, these are now the methyl group and my isopropyl group are on the same side of the double bond. So this one is the cis isomer, they're on the same side. Okay, great. Questions on that? You see that? Okay, I think this is something the more you practice it, the more you'll see that. So, okay, the next question in Alex, something that Alex will ask you is, it will ask you, can this exist as a cis-trans isomer pair? So what I like to do is just to draw it out, and then I know. So here we have, this kind of looks like, I would say that this is the cis isomer because our methyl groups are on the same side. So you have to redraw it and see if it's the same molecule or if it's a different isomer. So this one I'm going to draw over here. I'm going to draw, so I have OH, CH3 double bond. And then I'm just going to flip these groups. One is going to go on the top. One is going to go on the bottom. So if I draw this, then can you see that this one is the trans isomer? These are across from each other. I should draw C. These are on the same side. This is the cis isomer. So this can exist as a cis trans isomer. Do you see that? Okay. Okay, so then let's go over to this one. This one's a little bit hard to see, so I'm going to draw this twice. I'm going to draw it like this. So that's a Cl. Double bond C, H, H. That's a Cl. So if I flip this one, that's the only one with two groups. Is this a cis trans isomer pair, or is this just the same molecule? Yeah, this is just the same molecule. If I pick this one up and just flip it back over on top of itself, this is just the same molecule. This is not a cis trans isomer. So this one can't exist as a cis trans isomer pair. You see that? Okay. Let's see, how about this one? So this one, we could have our chlorines on the same side and our hydrogens on the same side. Or we can flip one of them and lock one of the chlorines on the bottom and one of them on the top. So this would be a cis isomer and a trans isomer pairs. So this one's on this side. This one's on the same side. So that would exist. Okay, how about this one? What do you think? Can this exist as a cis trans isomer? Yes, good. Good. And we kind of have like these two are just, one's the cis isomer, one's the trans isomer. Okay, great. So that's one of the topics. And let's see. So I think now we are going to talk about the reactions. So we're going to talk about reactions with alkenes. We're going to talk about addition reactions. So overall, what is happening in an addition reaction is usually double bonds are a little bit reactive. We have a lot of electrons right here. And so you're going to take a molecule, you're going to break this bond, you're going to break the double bond on the carbon, and then these groups, or atoms, are going to add one on each carbon. That's the basis of an addition reaction. So in organic chemistry, we have all sorts of addition reactions. We're going to talk about hydrogenation and hydration. But we have these other ones, halogenation, if we're adding like Cl2H2Br2I2 across the double bond, that's called halogenation. We can also have hydrohalogenation if we're adding like HCl, HBr, HF across the double bond. So this is what, if you take organic chemistry, this is what organic chemistry is. A lot of. You get a list of different reactions, and you have to remember how these will add together. And there's some theory behind it. You look for patterns, you look for rules. You can also do some, it's called electron pushing. You show where's their electron dense areas, where's their electron poor areas, and that helps you predict where these different groups are going to end up. So this is just like a super brief preview of organic chemistry. Okay, the first one we're going to talk about is a hydrogenation reaction, and this picture is on your notes sheet. Have you heard of hydrogenation before? Hydrogenation. Have you heard of hydrogenated vegetable oil? No? Okay, great. That's okay. So this is like how they make margarine. They take some oils and then they put a whole bunch of hydrogen on it, and that's hydrogenated. These double bonds, we talked about, those are unstable. So if you have fats that have lots of double bonds, they can go rancid. So one way to keep them lasting longer is to get rid of the double bonds. You can do that using hydrogenation. So we start with a double bond in alkene. We add hydrogen, H2 gas, and then we use a metal catalyst, and then we get this, the double bond goes away, and we got hydrogen added to our double bond. So then we get an alkane. So we need a catalyst. Usually we use palladium on carbon. We can also use platinum or nickel. So the catalyst just makes this reaction go faster. Usually what the metal is doing is giving the hydrogen gas a spot to break apart. That hydrogen bond just needs a little bit of help to go a little bit faster. And then something that's really important is that we need one hydrogen molecule for every double bond that we are trying to get to become saturated with hydrogen. So one hydrogen for one double bond. Okay, so if we have something like this, both of these molecules have two double bonds. So if we're looking at the first reaction, how many molecules of hydrogen are we going to need to change that to an alkane? 2, yep. So for each of these double bonds, we're going to need one hydrogen molecule, so we're going to need 2 hydrogen molecules to saturate that double bond. Okay, great. All right, the next thing that we need to talk about is hydration. So this is we're adding water across the double bond. So what's going to happen is one of the HO bonds is going to break. One of the double bonds is going to break. And then we add hydrogen to one side, and we add OH to the other side. So in this molecule, ethylene, it's identical. So it doesn't matter where we put it. We have to add some kind of acid to make the reaction go faster. That's called an acid catalyst. This is showing sulfuric acid. We can also just write, instead of like sulfuric acid or phosphoric acid, we can just write H+ on this arrow, and that shows whoever is looking at this reaction that you are using an acid catalyst to make this faster. And if you take organic chemistry, you'll talk about like the mechanism, how that helps make the reaction go faster. Okay, so the other thing we need to think about is we're going to predict where is the OH, where is the H going to end up. And this is based on experimental evidence. This is what really happens. If the carbon atoms are not identical, then the OH group is going to go to the more substituted carbon. So we're looking at the 2 carbons on the double bond, and we look to see which one has more groups on it. That's where the OH is going to end up. Okay. So here's an example down here, and that's called this person discovered that, this Markovnikov's rule. So here we have propene. We have one of the carbon double bonds has just 2 hydrogens. So these is the only 2 places that the OH could go. This carbon has a methyl group. This carbon just has 2 hydrogens. The OH is going to go on this carbon because it has more substituents. It has more branches. So then the OH ends up over here. The H goes over there. Okay. And that's just that's based on experimental evidence. Usually what happens is you get a major product. So that would be our major product. And then we also usually get a little bit of a minor product. So usually we get some kind of mixture. And again, if you take organic chemistry, you'll talk about why is this the best product? Why would that be the major product? And it has to do with when it's reacting, what things are electron dense and which ones are electron poor. Okay, so if we have something like this, and we are adding, so this is a hydration reaction. We're adding, this is, where is the OH going to end up?
It'll bond the same carbon as the CH3.
Good, yes, it'll bond right here. So there's only 2 places it could go. We're just choosing this carbon or this carbon. It's going to be perfect, according to Markovnikov's rule. So then usually we have to draw the product. And so we'll just draw something like this. So we have our methyl and our OH. And then we don't have to draw the hydrogen here because it's a skeletal structure. So if it was a condensed structure, we'd have to show that. But we don't have to show the hydrogen, but the hydrogen didn't end up right there. Okay, another type of question in Alex will ask you something like this. It'll ask you to predict the reactant. So based on this picture, what alkene could we have? So this is a little bit hard to see. This is a methyl group, and the OH are also coming off of that. Do you think you have an idea of where it could go? Or where the double bond would be?
Could it be on the 3?
On the 3? So you're saying like here?
Yeah.
Sure, yeah. Yep, so this one actually could have quite a few different options. So basically the double bond has to be connected to this carbon, because that's where the OH ends up. But we could put and then we have this methyl. So we could put it here, okay? What about this? Could this also work? Tell me if this could also work. Okay, and what about this one? Could this also work? Let's see, 1, 2, 3, 4, 5, 6. Okay, I'm just making sure I'm counting my carbons. What about this? Would that also be an option? So this Alex topic will allow for multiple answers, okay? So, yep, our double bond could be here. If we have a double bond here, then the OH is gonna end up here. If our double bond is here, our OH is gonna end up here. That's more substituents. And if our double bond is here, this is also more substituted, so it's still gonna end up in the same place. So we can have a lot of reactants in the same hydration reaction give us the same product. Okay, I think that is it. Yep, that was it. Okay, the rest of the time is yours to work on either Alex chapter 13, the lab 34. You can start reviewing for the final if you're done with chapter 13. What else? You have your signature assignment, don't forget to do that. Don't forget to bring your lab book back once you're done with the labs. Okay, questions? All right.